Sergey, thank you very much for the kind introduction and the possibility to give a presentation in this conference. And I'll try to share screen. I hope this works.
Yes, it works.
And I'll go to presentation mode. Still fine?
It's still in no, it's not in presentation mode. You have to start your presentation. So go to a slideshow and then yeah.
Okay, so
no.
let's see. So try again.
No worries, take your time.
So is that now better?
Not really. Yes. Well, we see. Right.
So is it now?
Yeah. Okay. Now it's in the presentation mode. Yeah.
Okay, cool.
That's fine.
All right. Yeah. So today the talk will be about soft quasicrystals, which are formed by polymers, and I will give a short introduction to quasicrystals, then talk about market dynamic simulations of very simple non-metallic quasicrystals, then comparison to experiments. This is going to be quite short about polymers and small angle neutron and X-ray scattering to determine those quasicrystals, and then a comparison to metallic and other non-metallic quasicrystals. And the goal is at the end to provide some unified geometrically based understanding of the formation of quasicrystals. So quasicrystals were discovered by Dan Shechtman for an aluminum manganese alloy in 1982. And he discovered this with small angle electron diffraction, where he recorded a diffraction pattern of 10-fold rotational symmetry, which is crystallographically forbidden. So he had quite a hard time at the beginning defending this against Linus Pauling. But meanwhile, it's well accepted that quasicrystals are an ordered state of matter. It's in those times defined as a metallic phase with long-range orientational order and no translational symmetry. And to understand this a little bit better, we have a short introduction into how geometrical objects can pack. So if we have a simple equilateral triangle, we can pack 3 others next to it. And if we continue to do this, then we will be able to fill a plane completely with triangles. So filling a plane completely with a geometrical object is a first thing that we have a look at. The next thing is then, if we have filled the plane, to look for translational symmetry. And that means we shift this lattice by a translation vector t, and then it overlaps with itself. So if this is fulfilled, then we have a planar geometry with translational order or periodicity. The third thing to look at is orientation order, and in this case, bond orientation order. So we draw an arrow or vector between 2 of the vertices, and then we rotate this, in this case, by 60 degrees, and then it overlaps with itself. And this means we have a six-fold rotational symmetry. So this is the third thing to look at if we have ordered structures from simple geometrical objects. Like with this triangle, it fills the plane completely. It has translational order, meaning periodicity, and also bond orientation order. This is not only the case for triangles, this is also the same thing for squares. and also for hexagons. So you could pack a plane completely with them, and there are no voids in between those tiles, and there's translational and orientational symmetry. So these are the three things we look at to describe simple systems. So how about the pentagon? So this is a pentagon. Also here we could place 5 pentagons next to them, but the problem becomes already obvious. They don't really completely fill the plane. If we continue tiling pentagons together, we will be left with voids. But one could consider that also the voids would be a tile, like a small thin romb. And then the question is, could we completely fill a plane with just a pentagon and those thin rhombs? And this is indeed the case, so you can do this. So this is one thing where you would have a completely different tile system, which completely fills the plane. The next thing is then to look on translation order or periodicity. So we try any type of vertex or any point even between the vertices, and we try shifting it, and we will never be able to have this in a superposition with the starting position. So there is no translational symmetry and no periodic order. So how about bond orientation order? So we could look for a point to rotate about. And if we rotate this by 72 degrees, which is the typical angle of a regular pentagon, we see it overlaps. So this is somewhat surprising, but these quasicrystalline tilings, and this is one example, have indeed bond orientation order, but no translational symmetry. And if we then position atoms, or it could also be colloids or polymer particles, on the vertices of these rhomb pentagon tiling, and we calculate the Fourier transform, then we get tenfold rotational symmetry. So you always get twice the symmetry if you do the Fourier transform. So this is the diffraction pattern that you would measure from this rhomb pentagon tiling shown on the left. So this just gives a brief introduction into what's special about quasicrystals. So they are ordered, but non-periodic. And the term quasicrystal was termed by Paul Steinhardt later after the discovery of quasicrystals. They have unusual symmetries, 5, 8, 10, 12, even 18-fold rotational symmetries are possible. They can be mathematically generated by projection from higher dimensional space. So say in 6 dimensions, they would then have translational symmetry, or via tilings. And today we will have the tiling approach to work with quasicrystals. In experiments, they are generally made by rapid solidification of metal alloys. And the most famous of these quasicrystalline tilings is the Penrose tiling. So at the right, you see Roger Penrose. He in recent years received the Nobel Prize, and he is standing on a floor tiling, which is the Penrose tiling. And you could imagine the headaches that the tiling specialist had to fill this because it's non-translational, and he probably did a hard work in order to get this Penrose tiling done. So, and I have a colleague indeed who has a Penrose tiling also in part of his home. Right, so short history of quasicrystals. In 1982, they were discovered by Dan Shechman. He was awarded the Nobel Prize in 2011 for this discovery. And meanwhile, there are more than 100 different metal alloys known that form quasicrystals. Surprisingly, there are also non-metallic soft quasicrystals. And nearly every year, there is a report of a non-metallic quasicrystal. It all started in 2004 with Cheng, Ungar, and Perchek, who synthesized dendritic liquid crystals and discovered quasicrystals with 12-fold rotational symmetry in those. So this was the very first report of a soft quasicrystal, which was not metallic, but it seemed a curiosity at that time. But since then, non-metallic quasicrystals are regularly discovered. So in star block copolymers by a Japanese group, in binary nanoparticle mixtures by Talepin. We discovered them in block copolymer micelles more than 10 years ago. Mesoporous silica, block copolymers, nanoparticles, colloid clusters, even surfactants form those kind of structures. And so it seems quasicrystal is really something quite general, not special to metal alloys and based on complicated quantum mechanical interactions. If those simple soft matter systems can form quasicrystals as well, there's this open question why they are formed and why they are stable and why they occur over so many different kinds of materials. So the question is, why would they be stable? And in 2007, there was the first report by Lifshitz and Diamond, who looked into a theory for two-dimensional quasicrystals. And they concluded if this is a non-metal, then you need two conditions to make a quasicrystals. You need two intrinsic different length scales, and you need three-body interactions. So if one looks as a polymer scientist, what you could then do, you could use core shell particles, and this could be just simple block copolymer micelles with a micellar core and a polymer shell. And then the two intrinsic length scales would be the core and the shell diameter. And in principle, they could then form quasicrystals, probably depending on the length scale ratio. As a college scientist, you could also think of binary particle mixtures, could be nanoparticles or even colloids with two different sizes. And if the size and number ratio would be right, you could possibly form quasicrystals. And also tetrahedra have two intrinsic length scales. This would be the edge length, but also the distance from the center to the face. And if you pack two of them together, then the two center distances would be the second length scale that you could have. So this would be a third example of a simple geometrical object with two length scales, which could potentially form quasicrystals. So today we are interested in why there are various different kinds of soft quasicrystals, what's the relation to metallic quasicrystals, and if one could learn from the simple soft quasicrystals about why quasicrystals would be stable. Of course, the hard matter metal guys would not like the simple-minded soft matter guys to explain to them why quasicrystals would be stable. So we started to do some MD simulations to learn about at what length scale ratio simple core shell particles would form quasicrystals. So we have say the core here, which could be a micellar core, it could be a nanoparticle that is coated with a polymer layer, or it could just be a surfactant micelle, where you have a certain diameter of the core sigma and a certain overall diameter. And as the ratio that we're interested in, we take lambda, which is the ratio of the overall diameter divided by the core diameter. So this is typically something larger than 1, typically between 2 and 3. We would then, for the simulation, need an interaction potential. To get quasicrystals, people usually use multi-well potentials, where they artificially design this multi-well potential to have maxima at the positions where you would have an FCC or BCC packing in order to destabilize this, and then end up with different other kinds of phases, which could be quasicrystals. In our case, this is clearly not an appropriate potential. So therefore, we took the Witten-Pincus potential, where we use a hardcore repulsion of the cores and a soft shell repulsion of the polymer shells. So this is a very soft potential, just logarithmically depending on the distance. And this is one which is known to describe the interaction of micelles quite well. So we did this with a graphic card and a desimulation package from Sharon Klotzer's group. And then we get a phase diagram, and the phase diagram is parameterized in terms of lambda. So on the x-axis, lambda around 2 would mean the diameter of the shell and the core are the same. And if lambda gets larger, you have cores with quite a large shell. And on the y-axis, you have the volume fraction of the cores. So that means at the lower left, you have a dilute solution of micelles that don't touch or overlap. And if you go to the upper right, you will have overlap. You're above the overlap concentration. You squeeze the shell, and the shells and the particles then try to pack in some kind of ordered or maybe quasi-crystalline lattice. The phase diagram I will be showing to you is very complicated. So it's surprisingly complicated, and therefore we go through it step by step. First, the stability regions have a funny hyperbolic extension, and this goes as lambda to the minus d, where d is equal to 2 for two-dimensional arrangements in a plane, where we just looked at, or 3 if we look at a three-dimensional system. And then we have a look and we see that depending on the size ratio and core volume fraction, we see the usual cubic phases, FCC, BCC, HCP, and also simple cubic. And we realize that they have many different stability regions. And this depends on how much the shells are squeezed together. And so this is something unusual that we have here. Many different of these cubic phases appear in this phase diagram. The next interesting thing is some highly unusual phases, like the HP10 phase, the CP4 phase, the BC8 phase, A5. So I must admit, as a polymer scientist or soft matter guy, this were the first instances in my life that I have to deal with such kind of funny and complicated phases. They have one thing in common. They're all high pressure phases. So they're high pressure phases for tin, for manganese, for silicon and lithium. And this is something remarkable that we will come back later. So this is some kind of high osmotic pressure at high concentrations of these micelles, which squeezes them together, and they try to find some strange way in order to form an ordered structure. So we recognize that Engel and Klotzer reported these already in some MD simulations some time ago, but using attractive multival potentials, we now find them with just a simple core shell repulsive potential. And sure enough, we see quasicrystalline phases, and in fact, many of them. So we see a small, thin stability region of quasicrystal with 10-fold rotational symmetry, then also a low-density type with 12-fold rotational symmetry. Then we have some high-density phases where the shells are considerably squeezed together. So there is a high density with 12-fold rotational symmetry having a different structure compared to this one. And we have an icosahedral quasicrystalline phase. In addition, there is this A15 Frank-Caspar phase, which usually is in the vicinity of such quasicrystalline phases. So this is remarkable that just with a very simple core shell system, you do MD simulations and you found stability regions for many of the most common quasicrystalline phases. One thing to observe is a typical feature of these quasicrystalline phases in that you have a central sphere that is surrounded by a shell or a ring of neighboring spheres. And this packing arrangement of a central sphere, which has an arrangement of other spheres in the immediate vicinity, is a typical thing for quasicrystal packing of spheres. We also did the two-dimensional phase diagram, and also here you see as a function of the size ratio and the core volume fraction or area fraction, quasicrystalline phases. So this is a low density phase with 12-fold rotational symmetry. Again, also a high density phase with 12-fold rotational symmetry, and one phase with 8-fold rotational symmetry. So altogether, in 2 dimensions and 3 dimensions, in these MD simulations, we find 7 different quasicrystalline phases. And in fact, these are the 7 types that have been found also for metal alloys. So with the simple system, we find all the types of quasicrystals that are known since the early days in 82. So this is quite remarkable with such a simple system. So the question then is, if you have this two intrinsic length scales, how does this translate into a structure or distances between particles or atoms? So if we have our core shell system, if the shells interdigitate or squeeze together so that shell edge would be in contact with the edge of a core, then we would have a small distance between the centers. And if just the outer edge of the corona or shells touches, we would have a large distance. And so in this way, this intrinsic two length scales of the particle translates into two length scales of a sphere or particle packing. So if we have a look now in this three-dimensional phase diagram, it's not immediately obvious how in 3D or a 3D structure could be realized with two length scales. So what we did is that along this line here, we plotted the radial distribution function of the structures. And you see here, this is the small distance. If you have the core shell contact, and this would be a core-core contact, these would be the small distances, and this would be the large distance. And what we see in the red lines, which is either a classy region or a quasicrystal, that indeed, even in 3 dimensions, these systems try to realize the two length scales. And even if you go to very large distances, like here, you see this prominence of the two length scales. So if we increase the volume fraction, we have the length scale of the edge-edge contact of the outer shell, but we also see how we squeeze together the shell such that at the end, we nearly have a core-core contact as the second short length scale. So this two length scale thing is really important, and it's a typical feature of quasicrystalline structure, not only in 2D, but also in 3D. And that's a remarkable thing one could learn from such simple core shell particles. So we have a bit of a look into these 7 different quasicrystalline structures. So this is in 2D, so just an area, a plane that is filled with a kind of tiling. And the tiling for the low density Q12 phase is funny because you have a decoration of the tile, but no particle or colloid on the vertices. This is quite special, but you could tie these together. They all have the same edge length, and this kind of tiling, and this tiling is called the Stemphi tiling. And so this is the way these things are arranged, and this is the diffraction pattern that you get from this kind of structures. And they have been discovered previously in MD simulation for different kinds of potential, either repulsive or attractive. This is in 2D, the high density Q12 phase. This is quite simple. You have a square and a triangle. They have the same edge length. You pack them together in what's called the Schlottmann tiling. And then you get this kind of structure. You get the 12-fold symmetry diffraction pattern. And this is tiling that has been previously predicted with the core shoulder potential by doTERRA 10 years ago. So this is the tiling, quite simple one for the high density Q12 phase. This is the 8-fold rotation symmetry packing in 2D. Again, you have a square with a center decoration, and you have a thin rhomb. And if you tile them together, this is called the Ammann-Beker tiling. And if you do this, then you have filled the plane completely, and you have an 8-fold rotational symmetry. We're now coming to the 4 3-dimensional quasicrystalline structures. They consist of planes with tiles, and the planes are stacked on top of each other. And here the 2 tiles for this 10-fold rotational symmetry is a thick rhomb or fat rhomb with a decoration here. And this would be the small distance, and the edge would be the large distance. And this would be a thin rhomb, where the small distance would be this. This packed together is the Penrose tiling, which we had at the beginning. And to indicate how this is packed in 3 dimensions, we have a coordination polyhedron. So this would be the plane with the Penrose tiling, and this would be a pentagon. And if you rotate the pentagon here by 72 degrees, by half of it, then this would be the plane below. And then this would be an AB stacking of these Penrose tiling planes with some occasionally center particles in between. And this gives you the three-dimensional packing. And this is an icosahedron. And this icosahedron is a typical feature of the 3D packing of these systems. So this is how in 3D these quasicrystals are packed. This is the simulation for the 12-fold rotation symmetry. And we see here the tiling. And what we observe here is that before, if I go back, we had so here we had a 5+5 ring around a central particle in the 10-fold rotation. Here now we have a 6+6 stacking of neighboring particles. This is shown here. You have 6 around the central one. This is the Stempfli tiling, and this is the coordination polyhedron, where here you have the 6 ones, and then this is the next plane with the 6 ones which are staggered with a central particle in the middle, and this AB stacking is then the three-dimensional arrangement. So in the 10-fold rotational symmetry, we had a 5+5 stacking, and here now we have a 6 and 6 stacking, also staggered. So this gives some idea about the geometry behind it. This is now the high-density Q12 phase, typical feature as well, a central particle, but now surrounded by a 7+7 staggered ring of particles. So this would be the 7 guys around the central particle in a plane. And again, here you have an upper plane with this tiling. This is the Schlottmann tiling with 7 particles, and then a lower plane with the 7 particles staggered and a central particle in the center. And this gives this high density phase. This has never been discovered in MD simulations before, but Steurer, who is like a magician in quasicrystals, proposed that this motif somehow should also give rise to quasicrystals. Then finally, we have a quasicrystal, which is the 3D icosahedral phase. This is now not a AB stacking of planar quasicrystals, but a real 3D thing. It has in the center a tetrahedron, which is surrounded by a dodecahedron, an icosahedron, and then a polyhedron, whose Greek name I forgot, it's really long. But this was now the Zi-type cluster. And this is a typical metal icosahedral clusters known in metal alloys for decades. And that just simple core shell particles, which interact with a really stupid simple core shell interaction potential, show these complicated quasicrystalline structures is a real surprise. So we showed that with simple core shell particles, we could get all types of known quasicrystals, which gives us now the opportunity to do some experiments to explore this in more detail. So this is the short experimental part. It's just 3-4 slides, which are ever worth like something like 3 PhD theses altogether. This involves the synthesis of the block copolymers. This is a polyisoprene PO. They form micelles with the PI hydrophobic core and polyethylene oxide shells in water. And in a concentration range around 50 to 20%, we get gels, which are transparent, which you could shear orient and study in rheosans or rheosacs, where you get then many diffraction patterns. So when I began small angle neutron scattering and I was doing these experiments, for example, at ILL Grenoble, all we did is measuring like a Q to the -4 porrod asymptote, and all the diffraction and solid state crystal guys looked at me and thought this is the most boring stuff which they have ever seen. But now we also have considerable number of Bragg peaks and even quasicrystals. So after such a long time, this is really satisfying. What we observe with rheosans is that if you shear orient the sample between 2 plates, and then first you have at high temperature an FCC packing. This was well known for these block copolymer micelles. But if we cool down, we see a phase transition to this phase with 12-fold rotational symmetry. And this is the quasicrystals that we were after. We now compare this phase transition that we see in the experiment. Could start the simulation. Okay, so before I screw this up, this is the phase transition that we see in the experiment. So you have the 6-fold rotation symmetry FCC. Then we cool this thing down. We see peak broadening. Then we see additional 6 peaks coming in between the first one. And then after a while, we have this 12-fold rotation symmetry phase. And in the MD simulations, you could do the same thing where you change the temperature, and then you see the phase transition from the FCC to the quasicrystalline structure. So this is pure self-assembly, no trick, just having such kind of a phase transition. Then the second system we investigated because all the people told us, oh, these are just stupid block copolymers and they can change aggregation numbers. And it's in water, it's probably specific. We went to a different system. This is now polyisoprene polystyrene in diethylphthalate, which is a high boiling solvent. So we now avoid anything which is related to drying artifacts while doing rheosans and rheosux experiments. And indeed, the same thing here. So this is in this solvent thing where you need to increase the temperature. So we start with a shear-oriented FCC phase. We heat it up, and sure enough, we get this phase transition to this low-density Q12 phase. And if we keep on heating, we have the expected phase transition to the BCC structure. So this works very well, just according to the phase diagram. For a different system where for sure we don't have specific aqueous interactions and no drying. Then the people come and tell you, oh, you have the aggregation number and this could be a non-constant if you increase the concentration or change the temperature. And this might be some reason why you have these things appearing. So we started using nanoparticles. These are iron oxide nanoparticles, and they are coated with polystyrene. And in this way, we assure that the core size is always the same, and also the shell size is always the same. We again go to concentration, which in weight percent, because you have this high density iron oxide nanoparticles, is quite high. So 50 to 55 weight percent in diethylphthalate, you go from the disorder into the ordered phases. And sure enough, we increase the temperature and we go from the FCC phase to this LTQ12 phase with 12-fold rotational symmetry at different concentrations even. So we're very sure we have these phases observed in experiments with very simple model systems, which are just block copolymerizers in water or just polymer-coated nanoparticles. Then we could go into the phase diagram. And what we observe is a really good agreement between the position of these FCC Q12 transition in the MD simulations and what we observe in the experiments. So this is our polyisoprene PO in water, FCC Q12 phase transition. These are the 3 data points in quite good agreement with the prediction. This is the polyisoprene polystyrene in diethylphthalate, and this is also in good agreement, and the nanoparticles coated with polystyrene also good agreement with the prediction of the phase diagram. And this is remarkable because it's such a simple system and such a simple potential, and it gives this remarkable quantitative agreement of a stability region for a quasicrystal. So we think we're pretty sure that this intrinsic two-length scale core-shell story is a real fundamental thing to investigate why quasicrystals are stable. But of course, the solid state guys will always give you a hard time and say, well, this is something special for your system. Doesn't have anything to do with metal alloys. So the next thing we did, we went through literature, and with nowadays double corrected transmission electron microscopes, people have a really good idea about the structure of also metal alloy quasicrystals. So we went through literature and compared all the known non-metallic quasicrystals, where I gave you an overview at one of the first slides, and different metal alloys and their kind of quasicrystals. So we start always with the reference, our MD simulation, with this really super simple interaction potential, giving you, in this case, this low density Q12 two-dimensional phase. And this is a publication on tantalum tellurium thin layer. And this is the quasicrystal which they observe. And remember, this tiling was special because the vertices were not covered with particles. And so what you see here is exactly the same Stempfli tiling. And you see exactly those tiles here. And you could tile large areas of this high resolution TM image, and you get this quantitative agreement. So this really shows you that the simple ND simulation gives agreement with even metal alloy quasicrystals. And this is by Zheng. This is the same Zheng of the Nature paper in 2004. So he still enjoys being in this business. And this is a Tiffany liquid crystal thin layer where they did X-ray diffraction of an ordered sample. And this is the structure they come up with. So I drew the tile structure on top of this. And this is really identical to this low density Q12 tiling. This is a direct connection between soft matter, and in this case, a liquid crystal, and a metal alloy, and this MD simulation. The second of these seven quasicrystals is the high density Q12 phase. This is the MD simulation. This is the reports from the Japanese group in the early 2000 years with block copolymers, also quite recently. And it's the same kind of tiling. This is a nanoparticle thin layer by Botnarchuk et al. And this is a fullerene monolayer. And this is an organo framework monolayer. And this is a colloid layer that reproduced at the air-water interface. So these very different systems, they all show this high density Q12 phase, and it's all in effect of packing and simple repulsive interaction. The third thing is then this 8-fold rotation symmetry phase. This is the computer simulation core shell particles, and these are the metal alloys. They are quite rare, but still metal alloys show exactly the same structure as the MD simulation for the core shell. So we really start building bridges between soft matter and hard matter in order to understand quasicrystals. This is now the fourth example. This is now in 3D, the 10-fold rotation symmetry phase. This is the MD simulation. This gives the Penrose pattern. This is a report in Science with tetrahedral nanoparticles, and I indicated at the beginning that also tetrahedra have two intrinsic length scales and thereby can form quasicrystals, and this is indeed shown here. This is the Penrose tiling that we also used here. This is zinc, manganese, yttrium metal alloy. This is aluminum, nickel, cobalt alloy. And this is aluminum, chrome, iron, silicon. These are, so this and this example, this is really the hallmark of metal alloy decagonal quasicrystals with high resolution TM. And you see the simple romp tiling quantitatively fits on top of this. And this is a naturally occurring quasicrystal discovered by Bindi, which I will come back to at the end. And this is a giant molecular blend where they also recorded decagonal quasicrystals. So also here, the same thing, simple MD simulation with core shell particles, non-metallic systems, meaning nanoparticles, and just big molecules, or just metal alloys, all the same thing. Fifth example, so because there are lots of enemies who will hate this soft matter guy telling them how quasicrystals form in metal alloys. Again, our MD simulation of the icosahedral phase. And this is high resolution TM of zinc manganese holmium alloy. This is another situation for aluminum, copper, iron. This is nanoparticles confined in spherical emulsion droplets, binary nanoparticle mixture, so non-metallic, and also simple spherically confined colloids form the same of icosahedral quasicrystals. So also here, it seems just packing, not a really special thing of metal alloys. This is the low-density Q12 phase, which we observed also in our experiments with the PIPO in border, the polystyrene isoprene in DEP, and the polystyrene-coated nanoparticle. It's the same as the thermotropic dendron phase reported by Zheng, Unger, and Perchek in Nature. It's exactly the same. You could just use the same tiling as the 12-fold symmetry phase found by Frank Bates and reported in JACS some time ago. Mesoporous silica, which is prepared by micellar phases from certain surfactants, so they keep this shape and then you reproduce the mesoporous silica. This is the first report. This is from Wiesner's group in Cornell, and this is a quite recent report. Also, they form this low-density Q12 phase. You could just come with the same tiling, tile decoration, and do this. And sure enough, this 12-fold phase is also observed for metal alloys, like for this work from Ishimasa, from Conrad. Now this is 1998 with the tantalum tellurium. This is again Bindi in PNS. Wang did a computer simulation now using real quantum mechanical interactions. We're having two length scales. They reproduce this kind of structure. And I mentioned tetrahedra. Also with tetrahedra, you could get this kind of AB-AB packing with the icosahedrons, which I showed before. So also here, it seems it's just pure packing, and it's resulting in the same kind of quasicrystal for metal alloys, for post-grafted polystyrene from the group of Cheng, and tetrahedral nanoparticles. Finally, there is this high-density Q12 phase, where you have this 7+7 staggered ring. So this orange circle is drawn around the 7 neighboring and the red one around the 12 neighboring ones, which give rise to this 12-fold rotation symmetry. This is the binary nanoparticle mixture from Falapin reported in Nature. This is another binary nanoparticle mixture from Ye and also Botnarchuk. This is another Stephan Förster from Halle, who discovered exactly the same kind of structure in a barium titanite perovskite monolayer. And this is a famous example from Ishimasa on nickel chromium particles. So also this high density Q12 phase is something that you observe in literature. And if you search literature for all these different examples, you start to see quasicrystals and this high density Q12 paper packing in many other things. And if you do this too much, you even observe this in pizza. So here you have a pizza with a central salami surrounded by 7, surrounded by 12. So it seems also that if you pack salami slices on a pizza, you could end up with this high density Q12 tiling, just as a word of warning if you overdo this. So finally, we wanted to see if this is something universal, applying to all kinds of different materials. And the only conditions would be that you have the two length scales and you would have the three-body interaction, which was proposed like nearly 20 years ago by the first people who looked into why soft quasicrystals would be stable. So it seems we have two intrinsic length scales, and they form two different length scales in particle packing. The short length scales, where you have the two cores closer together, and a larger length scales, where you have the two cores further apart. Having three-body interaction means we start forming triangles for these guys. And this is the usual way three-body interactions are considered in quantum mechanics. You just go through all the different variations that are possible. So you could have 3 triangles and all 3 have the short distance. This is then an equilateral triangle. And you could have 2 short distances, 1 long. Then you get this kind of triangle. And then you have 2 long and 1 short gives you this triangle. And of course, if all of them have the long distance, then you can have a free, an equilateral triangle. This is not sufficient for tiling, because for getting a tile to fill the plane, you need the edge length being all the same. So this wouldn't work because you have two different edge lengths. So you have to pack this thing together to get a square, and this thing with another one together to get a thin rhomb, so that you could start doing tilings. And so this is shown here. So this is the long length scale. This is the short length scale. This is how you would do the tiling of the two length scales with binary particle mixtures. And this would be the short length scale with the binary particle mixtures. Okay, so this works for both frequently observed systems. These are then the three triangles, which we just looked at before. And this is the example if you have binary particle mixtures. As said, the next step would be to put those together so that they all have the same edge length. So here you have the large edge length with the trilateral triangle, the thin rhomb. This would be the fat rhomb. This would be a fat square with the central particle decoration. This would be a smaller square with the short distance, which then you could tile with the short distance equilateral triangle. This is how it would look like with the binary particle mixtures. And then the final step is to put those tiles together and make a tiling. So if you put the thin and the fat rhomb together, you get the Penrose tiling, which is the low density Q10 phase. If you put those things together, then you get the low density Q12 tiling with this Stempfli tiling. And if you put those guys together, you get the high density Q12 phase with the 7+7 staggering, which would be the Schlottmann tiling. And also the Amann-Binka 8-fold tiling would work in the same way. So this was 2D. Now the interesting thing is the 3D arrangement. I told you about these special geometries here, which are the typical 3D packings for quasicrystals. So this would be the low density Q10 phase with the pentagon here and the pentagon here, meaning the central particle, and this theme of having a central particle surrounded by a shell of nearest neighbors is typical for quasicrystal packing. So this is the central particle surrounded by 5+5 tile, and this altogether gives a special kind of polyhedron, which is the gyro-elongated bipyramid, just that you once have heard this. So these planes are the Penrose tiling, and the overall thing is this bipyramid. If the distance between the center and the edge is the same, then this is the special case of an icosahedron, which gives rise to the icosahedral phase. This gives rise to the low density Q10 phase, and this would be a coordination number of 12, because you have here 1, 2, plus 2 times the 5. This would be coordination number 12. This is the LDQ12 phase with 6+6. Then this would be coordination number 14. This is again a gyro-elongated bipyramid with the case n equal to 6. And this would be the Stempfli tiling, which you need to fill those planes. And again, geometry, this is the high density Q12 phase with a bipyramid with now 7+7+1+1. So this is a coordination number 16 polyhedron. And then if you go on, you get this dodecahedron. So these are all the different polyhedrons that you get. This would be the polyhedron for your Q8 phase. And this is the domain of quasicrystals, meaning high volume fractions where you squeeze things together, where they start to realize high coordination number packings locally. And if you do this, then it's not possible to have a periodic tiling anymore. And this only works for quasicrystals. So quasicrystals like to realize those local arrangements at high volume fraction to realize high coordination number. If you deform this icosahedron, then you get a distorted icosahedron, which is the Van Casper phase. So this is not a perfect icosahedron, but now it allows you to pack periodically So this is a usual crystal, and also the efficiency would be similar. And a funny aluminum iron phase would be this example for coordination number 10 with N equal to 4. This is theta aluminum copper. This is the version of this bipyramids with N equal to 4. So this would be a staggered square around a central particle. And you could continue this, then a BCC would be the special case N equal to 3. So you see the whole picture emerging, that you have this bipyramidal packing, and for N equal to 3, 4, this is still possible to pack in a crystal, although this is very hard and this usually forms classes. This is the special thing about this, where it smells like you get near quasicrystalline phases, and then you have this area of quasicrystals, and it's just a story of packing spheres or atoms or micelles or fullerenes. There's an interesting analogy of these bipyramids to the Thomson problem. So this was something 120 years ago, where people thought about how electrons which repel each other would be surrounding a positively charged nucleus before the orbitals were known. So Thomson speculated that you would have a central atomic nucleus and 3 electrons, and because they would repel each other, the most stable lowest energy configuration would be an equilateral triangle. This would be the case 3. For 4 electrons, this would be a tetrahedron, this would be a bipyramid, and this octahedron would be the same thing for if you would have 6. Now, if you go on, then you see that for 10, 12, 14, you get exactly the same bipyramids that we propose for the packing of quasicrystals. So this seems really like the same idea. You have a repulsion here of electrons or of repulsive soft particles, and they try to get these local arrangements to minimize their repulsive energy. And it doesn't matter if these are electrons or if these are repulsive particles. So the orange things are the Thomson configurations. Here again, you see this theta aluminum copper, and these are the phases that we see in the quasicrystals. So this is a real close analogy, which tells us it's not just geometry, it's a geometry that minimizes repulsion, the same for electrons. Then this is the last part. This is just a very fascinating story of finding quasicrystals in nature. So there is this guy, Luca Bindi, who is a mineralogist from Italy, and in a museum in Italy, they did X-ray analysis of some minerals and found that in some meteorite, which was found in Siberia, there are traces of quasicrystal. Then they put an expedition together in 2011 where traveling to Siberia was still possible. So they went to this Katirga River, who is in the middle of nowhere in eastern Siberia, and in fact found again this meteorite, took it to the lab and made an analysis. So this is this meteorite material. This is an SEM backscattering image. And then you see different minerals like hollisterite, stolperite, katergit, and indeed an icosahedral quasicrystal. So in this meteorite, they found a naturally occurring, the very first naturally occurring quasicrystal, which was reported in 2009. They kept on searching for quasicrystals, and this meteoroid has something to do with making structures that survive super high pressures and temperatures. So this is this meteorite. So those guys went to the Trinity nuclear explosion site where the first nuclear bomb was ignited in 1945. And sure enough, in the middle of molten glass, they find an icosahedral quasicrystal. So the silicon comes here from the quartz sand and the copper from a power line that came down during the explosion and formed together with silicon this icosahedral phase. So again, super high temperatures, super high pressure formed this quasicrystal. And one must admire those guys. They went to Nebraska. There was a sand dune where during a lightning, there was a discharge, the power line was coming down, and they were looking for these minerals in sand, And they again found, in this case, the dodecanal, this is the low density Q12 phase of a manganese silicon alloy. So this is absolutely remarkable. And they speculated that this would be possible, this quasicrystal formation, by high pressure. So they did shockwave experiments and found that indeed you get those catechite phases and icosahedral quasicrystal. So this is remarkable because this story of high pressure and packing things together is something that quasicrystals make then possible. To go back to the connection to our kind of phase diagram of geometries, of course, they found this icosahedral phase, this is here. They also formed a decagonal phase in another report. And I must admit, as a soft matter guy, I really had no idea about holysterit, stolterit, and cartiagit. But if you look at the crystal structure, you see that those are identical to this funny aluminums irons, theta aluminum copper, and this BCC phase. So these are all these elongated bipyramids that you find in optimal local packing of things, being atoms, being colloids, particles, if they are squeezed together and have two length scales. So just finally, all these simple systems seem to follow this geometrical packing with two intrinsic length scales. So we have the core shell systems where you have as the two length scales shell and core diameter. You need to vary the density to get into stability regions of the quasicrystal. And there's a geometric relation between the volume fraction and the length scale. And this was for soft repulsive particles. For binary mixtures, the two length scales are the small and the large diameter particles. And in here, you have to tune the number ratio to get into stability regions of quasicrystals, again, repulsive. Then we had some examples of the fullerene or the barium titanate, and also the colloids in emulsion droplets. Here, the two length scales are the particle diameter and say the radius of the droplets that sets the two length scales. Tetrahedra I mentioned at the beginning. And finally, for metals, the two length scales seem to be the ion radius and the Friedel length. The Friedel length is an oscillatory length. That's something like the Debye screening of electrons in the quantum mechanical analog. And these oscillations that you see in this quantum arrow, they are these oscillations. Then you need to tune the valence electron density to get stable quasicrystals. And this is done by alloying. This is why the metal guys have this complicated ternary or even more complicated alloys. Similar, this length scale ratio depends then or has a relation to the electron density. And these are attractive oscillative potentials. However, one can show that by Boltzmann inversion, one can get a direct relation between them. So this is not a contradiction, but you could have both things together in order to form this two length scale repulsive interactions and minimize energy. So this brings me to the end. This was work over many years where Martin Dule, Tobias Jucik, and Thomas Kuhn from Bayreuth are involved. And I thank them. I thank the DFG for funding. And I thank you for the invitation and for listening.